In this last video, we're going to look at some exercises in which we are given the velocity or acceleration of a particle and a particular point, and find what the position function is. So let's find the position function given that velocity, which is always the derivative of position with respect to t, is given by 3t to the fourth. And maybe we know that the initial position of the object is 2. Well, then s of t is the indefinite integral, or the antiderivative of velocity, which in our case is the antiderivative of 3t to the fourth dt. And our power rule says that this is equal to 3/4, or sorry, fifths t to the fifth plus some constant. And this expression here, the fact that we know that the position of the particle is 2 when t is 0, will allow us to determine what exactly is that constant. What is its value? Because we know that 2 has to equal s of 0, and we have now a function for f of 0, namely 3/5 t to the fifth, and so this will be 3/5 0 to the fifth plus that constant. Well, that's just 0, so this is the constant. So now we know the constant is 2, and we could say that s of t is equal to 3/5 t to the fifth plus 2. Now given the velocity and a particular location of our function at 0, in this case, we know that the position function has to be 3/5 t to the fifth plus 2. Let's look at another example. Let's say that velocity, which is again the derivative of position with respect to t, is given by 3/t, and we know that s of 1 is 1. So then our position function is the indefinite integral of 3/t dt, which we know now is the natural log of, well, I need a 3 natural log of t plus a constant. And using this fact, we can figure out what the constant is, because 1 is equal to s of 1, which is equal to 3 natural log of 1 plus a constant. But the natural log of 1 is 0, so this ends up being the constant again. So s of t is 3 times the natural log of the absolute value of t plus 1. That's our solution. All right. Pretty straightforward, I hope. Let's do another example. So let's say that v of t, which again is our derivative of position with respect to time, is given by -3 sine of t. And we know that s of 0 maybe is 7. So then our position function is the indefinite integral of -3 sine of t dt. And so this is equal to -3 times negative cosine of t. where am I missing? Oh, plus our constant. And finding out what the constant is just by sticking that 7 and 0 in. So 7 is equal to s of 0, which is equal to 3 cosine of 0 plus the constant, which is equal to 3 plus the constant. Now notice this time in the other two examples, this term went to 0, but that's not always going to be the case. So here I need to solve for c. This tells me that 7 minus 3 is c, or in other words, 4 is our constant. And so our answer would be s of t is equal to 3 cosine of t plus 4. That is a unique position function whose velocity is this, and its initial position is 7. Now let's do one that's a little bit more involved. Let's say that acceleration. So let's say we're given acceleration. So acceleration, which is the derivative of velocity with respect to t, is given by 1 minus the square root of t. And we know that velocity when time is 4 is equal to negative 5/6. And the initial position, so position when time is 0 is 0. So given those two bits of information, let's find the position function. Well, first we need to find our velocity function. So velocity is the antiderivative of acceleration. So it's the antiderivative of 1 minus t to the 1/2 with respect to t, which will be t minus, so if I add 1 to this is going to be t to the 3/2. Then we need to multiply by its reciprocal, so 2 over 3 plus a constant. And we're told that negative 5/6 is equal to velocity evaluated when time is 4, which is equal to 4 minus 2/3 times 4 to the 3/2 plus a constant, right? Which is 4. So if I take the square root of 4, that's 2, but then I cube it, that's 8 times 2 is 16. And then I subtract that from 4. What this simplifies down to is that this is equal to what, negative, turns out to be negative 4/3 plus a constant, which tells me that the constant has to be 4/3 minus 5/6, which is equal to 1/2. So that's our constant for velocity. So we can say that our velocity function is t minus 2/3 t to the 3/2 plus 1/2. Then our position function will be the antiderivative of velocity, which we just computed. So this is the antiderivative of t minus 2/3 t to the 3/2 plus 1/2 dt. That's what our position function has to be. And running through this, that's going to be equal to, so 1/2 t squared minus 2/3 times, so there's going to be t to the 5/2. and I'll be multiplying by 2/5 plus 1/2 t plus a constant. And we know that when t is 0, so is the position. So we know that 0 is equal to s of 0, which is equal to 1/2 0 squared minus 4/15, 0 to the 5 halves, plus 1/2 times 0, plus d. Well, 0, 0, 0, so this is just d. So our d itself is, whoops, not d, but this is equal to d. So d must be 0. So now we can say with certainty that our position function will be 1/2 t squared minus 4/15 t to the 5 halves plus 1/2 t. And that's how we use the indefinite integral to find position functions once we're given velocity and or if we're given acceleration. We can use antiderivatives, and it points out, hopefully to you, that the importance of this constant c. Without that constant in either of these cases, right, without the constant here, I would not have been able to find a function whose derivative is 1 minus the square root of t and whose position when t is 4 is negative 5, 6. I had to have that constant to give us our velocity function. Right? I had to be able to add that constant 1/2. Now, in this one, because the constant became 0, wasn't as important, but in the other examples, hopefully it's clear that we've got to have that constant function. If you forget it when you write the indefinite integral, then you've done something wrong. You don't have the entire family of antiderivatives. All right, so that wraps up section 4.3. Happy mathing. See you next time.